Okay, thanks very much. And I'm going to tell you a little bit about the paper. First, I'm going to also tell you a little bit about what led up to it, and also some snippets of what has happened since. So it all started back in September of 2010. Tony and I visited Cynthia at MSR Silicon Valley. And there we met and had a lot of discussions with Omer Reingold and Moritz Hart. We spent a lot of time discussing computational fairness and reading some related work in philosophy and economics and law. And we struggled a lot with the definition at the time. And one thing we decided was that it wasn't enough just to remove the membership in some sensitive group. So S will be the variable that says if you're a sensitive group or not. We can't just remove that because of redundant encoding. So the other attributes can be used to predict that variable. Right? So that formed the key idea, the kind of assertion that we made in our paper, Fairness Through Awareness, which was that fairness requires the awareness of membership in your protected group. So that's shown here through, there it is, the Lady Justice with one eye open. And we also came up with a couple definitions of, types of definitions of fairness. The first one is a kind of simple, intuitive one of individual fairness, that similar individuals should be treated similarly. And the second is a group-based notion, where you have two groups, the S equals 1, S equals 0 groups, and they should be equal at the level of fairness. Actually, hang on one second. I think I just realized that I have the wrong slides up. Hang on one second. I'm going to do a quick change. That's why it didn't work there. Yeah, there we go. I had an old version. Back to it. There we go. All right, on to it. So two versions, you have the minority group, the S equals 1, and the majority, so that S equals 0, and you can equalize them in what's called statistical parity, which is the level of outcome Y, that they should both have the same marginal probability of Y equals 1. All right, so that's one notion of statistical parity. And working on this, we realized that our work did not have, that wasn't really a sufficient notion of fairness. And it was pointed out a few problems in the paper. So one idea is that, for instance, there could be subset targeting. So you could have a vendor that doesn't care at all about discrimination. Consider the case of targeted advertising. And the vendor could be targeting one subset within the minority group and showing ads to that group that they know they aren't going to click on, and that could justify future discrimination. All right, so fairness requires understanding of the classification task and understanding of the groups. We developed an approach to it where we had individuals that were mapped to representations, and then the vendor would get those representations and decide on the outcome, like are they going to show an ad or not. We assumed that we had a distance metric, some sort of metric that would say how close individuals were in the input space, and then we could satisfy individual fairness by making their representations or the distributions of representations that they were mapped to be at least as close as their distance in the input space. So let's assume that we have this task-specific similarity metric in hand, and that in our work we assumed that we knew that. And ideally this kind of metric would capture some ground truth, or at least a good approximation of it. And the nice thing about it would be open to public discussion and review and refinement. And there already are some examples of these kinds of metrics in use in lots of places, like in the finance and insurance industry. They have these, they're often secret metrics. In the healthcare industry, a way of kind of describing patients so that similar patients receive similar treatments. And an important question is always like, what attributes get included in these kinds of metrics? And Romer's somebody who works in, had a lot of influential work in kind of more on the social side, and came up with a definition of equal opportunity that's useful for social policy. And the idea here was that you might equate people that come from similar means and similar backgrounds, and then look at how much effort they put in conditioned on their circumstances. So in this work, we developed an optimization approach in LP that optimized the vendor's utility function, that took into account the, what kind of reward the vendor would get based on the kinds of representations were assigned to the users. And there was also this fairness constraints that had to be satisfied. So for instance, the Lipschitz constraint on the representations given the distances in the input space. And we had a group-based notion of this as well that was based on an earth mover distance between the distributions in the representation space versus the expected distance in the input space. All right? So let me give you a sense of, so this takes us up to like 2011 is when we wrote the paper, got published in 2012. Give you a sense of the kind of fairness zeitgeist at the time. At that time we found out that there were some other papers in the machine learning community, not in the machine learning community, in the data mining community on fairness. So in a different conference, the KDD, or Knowledge Discovery and Database Conference, there were a couple papers we found that were trying to look at fairness constraints and on classification. And then we decided to hold a workshop where we try to bring these communities together and also bring in some legal scholars and philosophers. So this is a proposal that we sent to NeurIPS in 2012. And I'll read a little bit to you. This is what we wrote. The aim of the workshop is to bring together people from computer science, philosophy, policy, and the law, try to tackle issues of fairness or information systems rely on machine learning and statistical inference. The goal is to inform the NIPS community about this intellectually interesting, practically important area, and develop machine learning approaches give greater, more precise effect to existing anti-discrimination law. So for this one, we invited speakers. The first two on this list are speakers from this KDD community who have written these papers, a couple people from our team, and then a couple legal scholars and philosophers who are working in this area. And the workshop got rejected, and the response we got was that we did discuss a lot about it, and our major concern was the amount of audience the workshop will get. So it got rejected. We kept working on it and came up with a paper that I'm going to tell you more about now. Learning fair representation. So here the idea was we wanted to cast the whole thing as a learning problem. And so they could generalize to new data and new individuals and learn some general mapping that could apply to anybody. And one of the key ideas was that we were going to learn a representation so that the distances in the learned embedding space capture the metric that's relevant to the task at hand. So effectively learning the metric was one of the key ideas. And that fair representation that would be learned would have some fairness properties that could then transfer and be used in other kinds of tasks. So we had this encoder-decoder framework that's familiar to everybody here now. And so the idea is that we have an encoder that's taking the input and mapping it to some representation Z, and then we have a vendor at the other end that's going to make a classification decision, like, is this ad going to be shown to somebody or not? And for that one, our main concern was the encoding. Okay, so we assume we have some vendor, but the main concern, the vendor may not care about discrimination or fairness, and so we wanted to have the encoding respect what's kind of the social good, so it have some sort of fairness notions encoded in the encoder. So we defined three aims for this encoder. The first one is that it should preserve information in X so that the vendor can maximize their utility. It should also preserve general information in X because, like I said, we want to take these representations and potentially use them in other applications, other tasks. Meanwhile, we want to lose information about S, about membership in the protected group. Okay? So this was like one of the notions of group fairness or statistical parity that could be defined at the representation level. So the probability of Z, that given that you're in the sensitive group, is the same as the probability of Z that the individual's not in the sensitive group. And for this, we took an information theoretic approach, and we had each of these as a kind of mutual information term. One maximized mutual information between the representation Z and the outcome Y, the maximize the mutual information between Z and the input X, while minimizing the mutual information between Z and S, the sensitive variable. So in true test of time spirit, I was coding this up. I didn't do that much coding beforehand or since. So I was using my MATLAB code. And I didn't do a great job. So the aim, the way we set it up, was that we were trying to think of it as in terms of encoding and decoding. So we're trying to learn some neural net encoding H that maps the input X to the representation Z. And then we're going to define these two other decoders. One of them is your kind of standard decoder from like an autoencoder, this F, that's going to try to reconstruct X. And the other one is another classifier that now is going to try to classify S given the representation Z, right? And so you can think of this as a kind of adversarial setup, because the G is trying to maximize the information about S, but we want to learn an encoding that minimizes the ability of G to do so. All right, so this actually predates GANs, and we set it up as this optimization. We were trying to minimize the difference between the prediction of X and X and maximize the difference between the prediction of S and S. All right, and we can do this in an alternating way, optimize H given F and G, and then optimize F and G given H. And I had a bear of a time trying to get it to work. It was unstable, and I thought that was my coding. So then we came up with a different version of it that was a simpler version that had some appeal. So in this case, Z is a kind of discrete variable. So think of it as it's kind of clustering the input examples, right? So each cluster makes some sense. And so this makes a lot of sense from our application point of view. If you think of the target advertising example, a cluster is something that the vendors care about. So they might want to target a particular segment of the population and send an ad to, I don't know, teenage urban males or white picket fence mothers, that kind of thing. And so now by making this a discrete variable, it made the minimization of this mutual information tractable, because all we need to do is really marginalize it out over X, which is tractable in this kind of model. All right, and then we can make it so that the marginal distribution for Z, given that you're in the sensitive group, is the same as the marginal distribution for Z in the insensitive group, and that will minimize the mutual information. So that's the term in our objective. We did a bunch of experiments. The first two sets of experiments were from the age-old University of California Irvine machine learning repository, the German credit, where we defined the sensitive feature to be age, and adult income, where we defined the sensitive feature to be gender, so we make them into these fairness problems that way. One thing about ICML that year, 2013, is they went with an experimental approach where they had 2 rounds of reviewing. The first round, some papers were either accepted or rejected, and the second round for papers were re-reviewed. So you got to revise and resubmit, and that was our paper. And so one of our revisions was defining this new data set, the Heritage Health data set, that was much larger, and it was a data set that took from Kaggle and made it into a fairness data set with a sensitive feature of age. I'm not going to show you all the experiments, but just one experiment just to give you a sense of what happened. So we compared it to some of these other methods I was talking about from the KDD community, where they were looking at statistical parity at the level of the outcomes and trying to match the groups at levels of outcomes. One of them by kind of massaging the labels and making the 2 groups have the same number of positive labels, and the other one is a kind of soft constraint, trading off the statistical parity with accuracy. So this was an individual fairness metric that we looked at after training and testing the models, and we found, so one way to look at individual fairness is to say the prediction for some example indexed by N here should be similar to the predictions of its neighbors. All right, so that's what this consistency metric is, and you can see that ours is in blue here to outperform these other models. Okay, so this is the actual open problem side that I had from that year, and the first one was that we wanted to further extend these intermediate representations and make them more expressive to go beyond the clustering. We want to look at other applications, like looking at eliminating demographic discrimination, deciding about transplant surgery. And then we wanted to further refine the definitions and the objectives of fairness. And so there's been lots of work in that area. I turned around soon afterwards and tried to reach out to people. I went and talked to some legal scholars and some philosophers and asked them for some ideas and what they thought in terms of fairness. And I found it just super difficult to try to encode and come up with a nice clean mathematical formulation of their ideas and the kinds of things they were doing. And that's an existing problem now. Okay, give you a sense of what's happened a little bit since then. There was a report done in 2014 by the Obama administration called Big Data, Seizing Opportunities and Preserving Values, and they concluded that big data technologies cause societal harms beyond privacy, concerned about decisions could have discriminatory effects even without intent, and subject already disadvantaged groups to less favorable treatments, and they were alarmed about the threat that you can get from this opaque decision maker and this impenetrable set of algorithms. And they looked for additional technical expertise to stop discrimination and more research into the dangers of encoding discrimination. So a lot of those lessons are still relevant. The field matured a lot. So our workshop, we redid it, submitted it in 2014, renamed it FAT-ML, broadened it to include fair accountability and transparency. And that ran for 5 years, and it spawned the Fairness, Accountability, and Transparency Conference, rebranded FACT. And then other conferences came along, the AI Ethics in Society, Foundations of Responsible Computing, and has a lot of research components dealing with fairness and those issues in computer vision, NLP, and other AI conferences. I went to a conference on data and civil rights, still trying to figure out, talk to these folks and see what, I was like a representative of the algorithmic perspective at this conference, where they were trying to bring people together. They were trying to set, their aim was understanding data-related criminal justice practices from different perspectives and creating connections between these different constituencies, ensuring that technology be used as a force for good. What I discovered there it had two insights, I'd say. One of them was I found that there was this deep distrust of algorithms. So I remember talking to a judge from Brooklyn, a longtime judge, and she was telling me that if I gave her an algorithm that had lots of different data that went into it and could be tested and ensured that it tried to discriminate as little as possible, and compare that to having a judge, let's say, I don't know, somewhere in Texas who is known to make very biased decisions, she'd prefer the judge. And her reasoning was because she knows the judge and she doesn't really know about these algorithms. And so there's that deep distrust, and I found that it was actually warranted in a lot of cases. So I spoke to somebody who had developed for the state of Pennsylvania the recidivism scoring that was being used in bail hearings for in Pennsylvania, and I was really shocked to find that they had done almost no real good quantitative validation of the conclusions that their algorithm was finding. So we continued working on our algorithms. We tried, as I said, come up with richer representations that were more expressive. One way of doing this is that we formulated an objective of trying to match these group-based latent distributions using an MMD objective. And another bit of work is that we came up with a much improved adversarial formulation that could handle fairness metrics beyond statistical parity. And we called that one laughter. So let me conclude by telling you about some of our current achievements and challenges, I think. So one thing, that the field has gotten a lot broader and has a much broader view of the underlying issues. So the intersectional fairness is something that people care a lot about now. We consider there's many sensitive attributes and a lot of them are overlapping. There's also the case of unknown sensitive attributes. So you might not, for privacy reasons or other reasons, not know they might not be observable. So this work here is work that was done on fairness considerations in the queer community. So not an observable characteristic. It's also very interesting links between fairness research and other areas, particularly robust ML. So this is a table we had in a paper my group did a couple of years ago where we laid out some of these parallels. And one thing in particular, I'll highlight one of them. So a popular work by IRM, invariance risk minimization. It turns out that a couple of years earlier, there was some very related work in the fairness literature. And so in IRM, the main objective is called the environment invariance constraint, where you want to make the expected value of the outcome Y, given condition on the representation, be the same across environments. And from the fairness point of view, that was called group sufficiency by Alexandra Chulchova and colleagues. And the idea there was instead of environments, you're dealing with groups. I'll put a little plug in for some recent work my group's done where we've taken some methods that we've developed from conformal prediction and used those to obtain some optimization and also guarantees on some novel fairness objectives. So then there's also been increased scrutiny of ML algorithms obviously since then. So this was like last week, the administration got buy-in from companies for exploring the risks of AI. And this is a lot like it echoes a lot the Obama thing from 9 years ago. And a lot of considerations of fairness and discrimination in there. And it's really a question now whether the companies will be open up and transparent and be able to be audited and tested by outside individuals. And also do work on the inside on this. Let me highlight the last thing. I'll highlight a couple bits of work I think they're especially interesting related to this work. So one is there's a line of work in the theoretical computer science community called multi-calibration, which is trying to achieve fairness across every computable group. And that's an impressive line of work. And there's also a separate body of work on participatory machine learning. So an example of that is some work on collective recourse by Elliot Krieger, Moritz Hartmann, and lots of others, where the idea is that people change their behavior and change the data and therefore affect the way a machine learning algorithm operates. And then also some other work on bias bounties by let's see, Mike Kearns and Aaron Roth and lots of companies trying to get people to participate in evaluating and auditing machine learning methods. A little call out at the end here. So the paper that won the best paper at this year's FACT conference was by the Queer and AI group called a case study in community-led participatory. Okay, so I want to thank my collaborators shown here, and thanks to the committee for the award, and thanks to all of you for listening.